In this chapter, we start to delve into energy, which is probably one of the most important concepts that we'll cover in this class. It's a concept that applies in all areas of science and engineering, and it's an incredibly powerful tool once you use it. So, I guess the one question we have to ask, really, right off the bat, is what is energy? This is one of these words that has a certain meanings in everyday English, but that tends to be very different than the very specific definition that we use in physics. Probably the most common statement of what energy is it's the ability to do work. Now, since we haven't studied work yet, it doesn't help us a whole lot, but another way of thinking of it is the ability to do stuff. It's the ability to make stuff happen. A good analogy with energy is the concept of money. What exactly is money? You can probably name off lots of different types of money, or things that are used as money, like credit cards, checks, hard currency. But defining money is a little bit difficult. Maybe the easiest way to define money, it's the ability to buy stuff or trade for things. And like energy, money tends to be a conserved quantity in that you can transfer it back and forth between different types. You can transfer money from bills that you have in your hand to electronic money that you have in your checking account, to purchasing bonds or stocks or something. But overall, you're going to have the same amount of money. The money that you have is conserved. So that's this analogy of money and energy is a useful one to explore when we're talking about what exactly this energy is. Incidentally, one site you might want to check out is called The Energy Story. It's kind of a useful overview of what energy is and what it means to us in our everyday life. It doesn't have a lot of very hard physics associated with it. It's much more how it relates to our lives. There's a link in the content section of D2L that you might find useful. So, according to relativity, the total energy of a particle with mass m is equal to gamma mc squared. So again, this is the total energy of a single particle. So it depends on the mass. Gamma depends on the velocity and c, and then we got c here as well. So this is everything. This is all the energy involved. Now, if the particle is at rest, that means that my velocity is going to be 0. If the velocity is 0, this term in parentheses is 0, and gamma just reduces down to 1. So we plug that into the equation, and we see that the rest energy of the particle is just mc squared. This is Einstein's equation that you've probably heard, E equals mc squared. This only refers to the energy of a particle at rest. And it's often stated that this is the energy associated with the mass of the particle. When we start dealing with things like fusion reactions or fission reactions, nuclear bombs, nuclear reactors, it's a conversion of mass that results in the large energies that are involved. So this equation, E equals mc squared, is kind of an equivalency relating mass to energy. Now what that means is that all of the rest of the energy has to be associated with motion. So if we take that total energy and subtract off the rest energy, what we have left is the energy of the particle relating to its motion. We call this the kinetic energy. And that's just gamma minus 1 mc squared. Now remember that gamma is greater than or equal to 1. So that kinetic energy is always going to be a positive quantity. If the smallest that gamma can be is 1, this term here ends up being 0 or larger. Now, a lot of times we will be ignoring the rest energy of the particle, but for right now, here is an example of a bar chart, an energy bar chart, something that we'll be using. And so what we've done is we represent the total energy with a bar. The height of this bar is related to that energy, and we see that it's comprised of the rest energy plus the kinetic energy. Now, for most of the problems that we'll be dealing with, the rest energy is actually going to make up almost all of that bar, and so it might be more appropriate to draw rest energy that looks like this, and for very small speeds, my kinetic energy might make up only that top little bit. And what we'll see is that for most non-relativistic particles, we can actually ignore any changes in the rest energy. Now, for low speeds, in other words, if v is much, much smaller than the speed of light, we can approximate our total energy. We can approximate the equation gamma mc squared as roughly mc squared plus 1/2 mv squared. This clearly is the rest energy of the particle, which means that this term right here has to be equal to the kinetic energy. So the low speed approximation for kinetic energy is 1/2 mv squared. One thing I do want to point out is that since v squared is always positive, kinetic energy of a particle is always positive as well. So K will always give us a positive quantity. Now, energies, and we'll find out work, can be negative, but the kinetic energy itself will always be a positive quantity.